of that, the property you get at summer time is different, and I mean winter time will be different. So you get like an inconsistency, I mean, in the properties. So to get rid of all those stuffs, people go out with this kind of stuff like mimicking the same sequences, amino acid sequences, with the help of cloning or some sort of like a biofermentation technique. That is called a recombinant protein. Okay. So if you do that in the lab, I mean, artificial way, the properties will remain, I mean, throughout the same. I mean, consistency will be there. So that answer I expected, that was missing from your answer sheet. Okay. And here the first question, derive the structure property relationship of styrene, butadiene rubber, and with respect to PVC homopolymer. It's very simple. I mean, you are written clearly. I mean, styrene is contributing for modulus, like mechanical properties, etc., and butadiene is giving for, I mean, contributing for the dynamic properties or the elasticity, etc. So one more answer is something like here, since you have this copolymer is ratio, you can play around with that ratio and you can have any kind of properties. But in case of PVC, you cannot play anything actually, since they are homopolymer. Like only vinyl chloride is there. So maybe you can play around with their molecular weight or the distribution or kind of entanglement. And apart from that, nothing you can play. So that one specific answer is missing. Although you have mentioned that this can be used for so and so pipeline application, it has got chemical resistance, etc. Yeah, when I specifically ask the structure property relationship, means the structure should speak actually. Okay, and this everybody have answered. I mean, since the polar and non-polar that incompatibility is there, because of that you get that excellent oil resistance in nitrile rubber. And yeah, recombinant protein, we have seen it. And yeah, beta sheet content. Yeah, that's fine. You have written fine. I mean, you have some, I mean, alignment of certain hydrophilic and hydrophobic interactions and the protein structure. And then you get the beta sheet, I mean, formation, which is secondary structure of protein. But how to characterize them? I mean, this is all like speculation. But how to characterize them? Test it. If you remember the lecture, if you have the more beta sheet content, you will have more mechanical properties, because beta sheet is, I mean, it's a kind of crystalline region or the, I mean, formation, crystalline content. Okay. So more the crystalline content in your protein, you will have I mean, very good mechanical properties. So one way, so you prepare the protein and then you study some mechanical properties, maybe of some rheology. Okay. You dissolve it into some suitable solvent and you can make some gel or something, and then you can measure, I mean, the viscosity, melt viscosity of the protein, and then you can see how the mechanical properties. Okay. If more the beta sheet content, I mean, you will have a, I mean, very good modulus or the viscous, high viscous, I mean, of your proteins. And the other way, I mean, since it is forming some crystalline content, you can do some thermal analysis, something like a DSC. Okay. So where you will get some sort of melting peaks or the kind of endothermic peaks actually. Some phase transformation will happen at in the proteins at certain temperatures. Okay, which you cannot observe with other proteins. Okay, because they don't have any kind of beta sheet domination. So that answer is missing. Well, and then yeah, briefly discuss about the drug release profile of a physically loaded one and chemically tagged with the carrier. So what's the difference? See, both is going to release, no doubt. So now the second question, how both get released actually? I mean, physically loaded one, how it release, and chemically loaded one, how it release.
There's the difference in stimulus, like in physical one, there is interaction with the physical stimulus, like,
Exactly.
and in chemical one, there is reaction with water or the enzyme.
Mm-hmm. Literally, like the basic fundamental is that, like physical loading, it's a interactions, like a secondary bonding interactions. Okay, so you need to have a little like high forces, I mean, to break those bond, I mean, between the drug and the carrier. Okay, so to kind of maybe a hydrogen bond interactions or the van der Waals force interactions. Okay, So slightly, if you play around the temperature or some sort of magnetic field, like if you stimulate those environment, the drug will automatically will start to release. But in case of chemically loaded one, unless until you go for very high, I mean temperature or something, the drug will not release because it was attached covalently. I mean, there's covalent bond interactions. So if you want to break those specific bond, actually, I mean, kind of some certain thiol-based bond, etc., they are very sensitive for laser light and all. So if you use some sort of laser light and laser, I mean, wavelength, okay, so you can specifically break those bond, and subsequently the drug will start to release. Okay, so it's a kind of whenever you want to release the drug, you can switch on the laser and the drug will release. And if you don't want to release the drug, you can switch off the light and the drug will not release. I mean, that much predominantly. But you cannot control that in the physically loaded one, because the moment when you increase the temperature, all the bond, I mean the hydrogen bond will start to, I mean, break, and as a result, the drug will release, I mean, vigorously. Almost all the drugs will start to release. Okay, so there's no control over the drug release in the physically loaded one, and in case of chemically loaded one, you can control those drug release content. So now today class we'll see like exactly, I mean, how to play around those drug loading efficiency, and then how much drugs can be released with the help of different external simulations. Okay. So anything else to discuss? I think it's okay. I mean, it's not so tough or kind of very easy. So any doubt to know from the mid semester questions? I'm not corrected. I'll finish it in 1 or 2 days and I'll upload it again in Moodle. You please go through it. Then if you get any doubt, we'll discuss. All right.
So how are the beta sheets characterized?
Was that? Who is
The
that?
characters,
Yeah, you are not there.
I
You missed
guess
it.
the yes
Okay.
sir, I missed
Okay.
it. Like
Fine.
just now I heard DSC.
Yeah, DSC, and you can also choose some of the mechanical properties determination. One of the example is rheology studies. So how you do the rheology? You have either parallel pluviometer or some viscosity measurements. Okay. So once you know that your protein is capable to form more amount of beta sheet formation, that means you take that protein and then you compare them with the other, I mean, commercial available other protein which doesn't form kind of beta sheet content more domination. So what you're going to do, you prepare certain solution concentration, maybe a 4% or 5%, where it forms some sort of gel actually. Okay. So because if you want to do the rheology, your material should capable to form gel actually. So once the gel is formed, then you take them for the rheology test, and then you do the, I mean, kind of increase the shear rate from the lower rate to the higher rate. Then you can see how the storage modulus is getting, how your loss modulus or the viscosity is increasing. Kind of whether you are getting shear thickening behavior or shear thinning behavior, etc. Okay. So with the help of that, if you have the more beta sheet content, then of course you will have kind of shear thickening behavior, because over the period of time, I mean, with the increasing shear rate, the viscosity will also increase actually. Okay. Unlike the other proteins, they not have those kind of, I mean, very good mechanical properties. As a result, you will have a shear thinning behavior. I hope you are aware of shear thinning, shear thickening, all those things, right?
Yes sir.
Okay. So in fact, one of the slide I showed you, like how to visualize the hydrogel, I mean, mechanical properties. Yeah, here. This is what shear thinning or shear thickening. You imagine this is viscosity. Of course, modulus cannot be compared to, I mean, the rheological, I mean, flow behavior. So you assume here the y-axis is viscosity. So what is this, shear thinning or shear thickening? So shear thickening. With the increasing this frequency, the viscosity is increasing. That means it's a shear thickening. Shear thinning means its viscosity will come down actually. Okay. So you can see here, the crystalline parts are more here in the L lactate, and that's the reason wherever you have a L, you can see the modulus, pretty much high elastic modulus was there during the rheology test actually. So those who have the amorphous core, you assume that here you have more beta sheet content, you have a lesser beta sheet content, okay? All right, so this is again it's the same explanation with the help of different nanoparticles. So the moment when you add the nanoparticles, how the viscosity or the mechanical properties is increasing, okay? So from there, you can figure it out whether the nanoparticle is really giving any kind of effect when you form the hydrogel out of these, I mean, materials. Okay. So if, say, for example, if the nanoparticles are not at all interacting with this protein or the hydrogel, so you will not have this kind of differences between these materials. Okay. So rather you get the same similar, I mean, the profile, I mean, rheology curve. Okay.
Okay, sir.
So yeah, all right. So this is kind of very complex structure. Huh? I don't know why. Something is missing over here. Anyway, so now we will see some of the kind of effect of different drug and their impact on encapsulation and their releasing characteristics with the different carriers. Okay, carrier means the substrate what you are going to take for loading the drug. Okay. So now we have kind of different substrate or the morphology. Okay, here you can see the thin film. I mean, kind of multi-layer structure or single layer structures, etc. And you can see some of the morphology, something called fibrous morphology. Okay, you have a fibrous mat which has different, I mean, oriented fibers. Okay, irregularly oriented. Okay, and then we do have a certain morphology called micellar vesicle structures. Okay. So what is micellar and what is vesicle? No idea. See, surfactant, you know, right? You have polar groups as well as non-polar group. Non-polar group usually forms as a tail, and the polar group usually forms as a head. Actually, the moment when you mix the surfactant in water or any organic media, what will happen? They will start to dissolve at lower concentration. But the moment when you go for the higher concentration, either they'll form as aggregate or they'll transform into the gel actually, because the viscosity will be pretty high. So in the in-between stage, they'll start to aggregate. So the moment when they start to aggregate, that means there are a lot of small that head and tails usually, and it forms as a small aggregate. So that aggregate usually called as a micelle. Okay. If you see, I mean, in the inner, I mean, portion of this micelle, you have a lot of head and tail. I mean that kind of combination like surfactant. Okay. That is called micelle. And if you go for higher concentration, you'll get a gel. And what is vesicle then? Vesicle means kind of you have a micelle and some of the portions are opened actually. I mean broken way, kind of core shell structures. So when it will happen, I mean when you mix, I mean different charges of surfactant, this kind of vesicle will start to form. Okay, because of those, I mean charge differences between those two surfactants. Okay. So, so let's see. I mean, so you assume that you do have these kind of morphologies exist in the polymeric structures, okay? And this is kind of 3D bioprinted structures, okay? And yeah, we didn't see this technology. I mean, the fabrication method we'll see maybe sometime later on. But you assume that this is one of the structures exist in the materials technology. I mean, 3D bioprinted structures using 3D bioprinting technologies, okay? Of course, these are also being used widely in the biomedical sectors. Okay. Now, we are going to load the drugs into these carriers, different carriers, films, fibrous scaffold, and then micellar vesicle, and then 3D printed structures, etc. And then we will study how the I mean percentage of drugs can encapsulate or get into this carrier, and how the drug releasing efficiency or the characteristic will be there. Now you can see here films where the drugs can enter. There's no space here. Literally, there's no space. So what will happen? The surface of the films only capable to absorb those drugs actually. So the drug, whatever you are loading, and they will start to attach on the surface of this film. And in case of fibers, where the drug will start to embed. Because you see here, this fibrous structures, you have a lot of porous structures. So if you measure these pores, they are, I mean, less than 2 micron or 3 micron. And of course, you do have some nanopores as well. So as a result, the drugs can also get into these porous structures as well as they also can attach on the surface of the fibers. Okay. So you have a lot of, I mean, different possibilities where the drugs can, I mean, get into the substrate. But in case of micellar or the vesicle, again, they also have a lot of force here, right? I mean, between the, I mean, two aggregate like micellar structures, you can see the formation of little porous structures, okay? Where your drugs can get into it and they can sit, I mean, nicely. I mean, they can able to bond well with the, I mean, carrier micellar. But in case of 3D printing, you have more option because you are printing the materials. That means you can add the drugs as well as to the materials, and then you can print the drug automatically. As a result, you can print as much as drugs you want. Okay. Now the question now, I mean, you do have a hydrogel. Okay, you can prepare the hydrogel. You can load the drug. I mean, either physically or the chemically. I mean, likewise also you can prepare the drug encapsulated carriers. So can you now rank which one has more drug loading efficiency now? Among these 5 different morphologies, one is film, fiber, and then micellar vesicle, and then 3D printed structures, and then hydrogen. The first one, which you feel we can load the drug more. Obviously, what? This is 3D printing here. So what is 3D printing? No idea. Maybe I'll have to go to some slide.
Layer by layer deposition
Exactly.
of the biomaterial.
Yeah, you are going to deposit the material with the help of 3D printing head, I mean, which is nothing but kind of extrusion-based nozzle. Either you can melt it or you can take in the form of dissolved materials, okay, kind of gel. And then you're going to fabricate those structure with by layer technique, okay. So like this kind of nozzle will be there. You put your material maybe in the form of hydrogel or some sort of melted, I mean, solid form, and then you can melt it, and with the help of those, I mean, a robotic dispensing system, this head can be movable at 3 direction, X, Y, Z, okay? And then with the help of this, I mean, CAD design, you can design your the substrate or the material, I mean, how you want to fabricate, okay? And then you can fabricate that, I mean, the product, whichever the design you would like to have it, okay? So as a result, you can take the material and then you can load the drug how much ever you want. So they can mix well and simultaneously you can, I mean, deposit on the substrate by layer, I mean, technique. Okay. And if you see the, I mean, the types of 3D printing, sorry, maybe it is the obvious slide one. Okay. So that is missing here. So likewise, you can fabricate any type of structures. You can see here, this is, I mean, blood vessel tube. I mean, which cannot be fabricated by using any other technique because this is 3D model. And if you want to fabricate this 3D model, of course, you should have that, I mean, kind of navigation. Your nozzle should navigate 3 direction, X, Y, Z. And of course, they also have fabricated this structure along with the blood cells, I mean, HUVEC-based cells. Okay. So now the priorities, I mean, the 3D printer structure can accommodate more amount of drugs and subsequently which one can be? Hydrogel, because hydrogel, during the preparation of hydrogel itself, you are going to add the drug and then you are going to, I mean, embed them in the hydrogel structure. As a result, you can incorporate more amount of drugs in the hydrogel. and followed by that micellar or the vesicle, because you can see here how much the pores presence in the even the single aggregate. Okay, and then followed by fibers, I mean nanofiber or the fibrous scaffold, and then followed by film-based substrate. Okay. Yeah, that's it. And we'll see in the next class like how to calculate the drag loading efficiency, sorry, encapsulation percentage, as well as how the releasing characteristic. Like we have a different phenomena, like kind of sustained drug release, and we have kind of robust or the burst drug release. Okay, so how to get rid of those burst release? I mean, burst release means the moment when you expose the drug carrier, I mean the drug embedded carrier, all the drugs, I mean 100%, almost 95% of the drugs will start to release in the first 2 minutes of the experiment. So that always not helpful, because releasing more amount of drugs at certain I mean organs is not at all helpful actually. As a result, you will have more side effect, and that drugs will not be preferred actually. So we'll see in the next class about those things. Okay. Mhm. Anything else to discuss? You have any class or what next hour?
Yes, sir.
Okay, Jintal. Mhm. Yeah, they are asking me to correct now. I don't know. This is really headache for me. Okay, I'll talk to Rana about this. Fine then. See you tomorrow. Day after tomorrow, sorry.